Hello, everybody. Welcome back to another Veloren Reading Club, which is in Rust, but the Rust meetups were this weekend, not now. Today we've got a super awesome topic. We're going to have Imbris come in and talk about graphics and particles today. And so Imbris is one of the core members of Veloren. They've worked on a ton of stuff relating to a lot of like the graphics pipeline and just like pretty much every other system in the game. I mean, Imbris has even done like a decent amount of work on like CI, which is where I do a lot of my stuff as well. And so Imbris is a jack of all trades. And we were talking about like what types of topics we could go over. And when Imbris mentioned the graphics stack, I'm like, this is like a really cool idea because this is something that to me is like a black box of Veloren. Like I don't know very much at all about the graphics pipeline works. And so, yeah, I think we'll walk through a bit of that today. So Imbris, I will bring you on stage and we can get going.
Hello. So
Hello.
Today I'm going to try to give an overview of the graphics layers making up Veloren's render, starting at our main loop and then just trying to dig down from there. And then after that, I want to look at some potential optimization that we can do in the particles system.
Yeah, I think this sounds like a pretty good plan. Yeah, we were talking a little bit about it before, sort of like the being able to step through some of the optimizations, and I'm quite curious on how we'll do it from like the graphics perspective. So yeah, we'll see how it goes.
Okay. So this is the run function in Voxygen, and it's sort of the core of our main loop in Voxygen. So this is like a stack of play states. So these are like the main menu, and then the character selection and the in-game session. And so this is the main loop. So the loop is actually driven by winit. So we provide this callback, and then winit feeds us events, and we respond to them. And since we want to control how long we sleep in between polling for events, we use this control flow poll. So when it will always return the control to us instead of waiting for an event or so when you can set it to wait for a specific amount of time or wait for the next event to occur, but we just want it to just always return control to us, even if there aren't any events.
So is this like once a frame, or is it like when you have any mouse input or anything?
So frames are defined by when we get the, frames are controlled by the main events cleared event. So when we get to this event, we will perform all of our work and then render a frame. And then we will we'll block the main thread by sleeping in our own code until we want the next frame to occur. And while that is happening asynchronously, events are going to be generated. And then once our sleep ends, our sleep is going to be here-ish. Yeah, here.
Okay. And is that like where the global state clock is happening?
Oh yeah, right here. When we tick the clock,
yeah.
When we tick the clock, that's when the sleep occurs.
Okay.
Yeah. So once the sleep is over, we will we'll maintain the global state, and then we will return control back to this so here the main event's cleared, and so we've handled the main event's cleared event, and so then this closure will exit and control goes back to win it. And so while we're sleeping, like events occurred like key presses and stuff. And so then when it will gather, we'll take those events and then call this closure with all those events that it has. And then we will handle them. So like if the window was resized, we'll get the resize events. And so we know we're at the start of handling events when we get the new events event. And so we use that to add some to start a Tracy span so we can profile how long it takes to handle events. And then, so like say we get this window event and we'll collect the window, we'll collect like key presses and stuff and then handle them later. So, and then, so we handle all those events and then eventually when it will send us main events cleared, which means all the events were passed to us, they were available. And then we'll run the body of our main loop. And there's some interesting stuff like this bug on macOS where we have to skip every other main events cleared. So basically we run the poll cycle twice before we do anything because there's a bug where we don't get mouse motion events if we don't do this.
Interesting.
But it doesn't really affect, like, it's not like a significant overhead or anything to run it twice compared
It's
to
a fun little quirk, yeah.
Yeah. So
it's surprisingly simple. Like that's not that many cases of what events you have to handle. I would have expected it to be like way more or like way larger for this like sort of ingress of stuff every frame from the window.
Yeah, so like all the stuff that we really need to handle are these window events and the device events. And so we'll take those and feed them to our handler methods on the window here. Here. So you can see like here is where we handled the device events. Oh, so the only one that we handle is mouse motion, which is what's used to control the camera. So what we'll do is we collect events up into our own, just like a vec of events, and then when we run them by our main loop, we'll actually consume them all at once instead of like feeding them down one at a time. And then here's where we get window events, and so like the window is close request will close. If it's resized, we'll say okay, it resized, and then so this is a bool, and then so later we'll check, and if it's true, we'll get the current size of the window and resize all of the things that need to be resized. Recreate the surface. And then scale factor changes. The window. This would be. I'm trying to. Isn't when the window's moved? I don't know what we would do with that. And then if we this would be character. And a mouse input. This is where we get like clicks from the mouse. This is modifiers. So these are like modifier keys like control and shift. And then this is all keyword input. And when the window's unfocused to focused, the mouse moves and scrolling with the mouse. So going back to the run function. So this is the body of our main loop where we handle, so it's just called handle main events cleared. And this is here we will generate events for, we will so like the screenshot key and full screen toggling can be like pressed multiple times in a single frame, but we only want to handle that once instead of like trying to do 100 screenshots for one frame or toggling full screen a bunch of times.
Yeah.
And so then here's where we handle the states. So these are so right here is actually where we tick the state. And then it can return continue, shut down, pop, which removes it from the stack of states, add a new state, or switch to a different state. So switching will remove the current state from the stack. Pushing will just put another new state on top. So this state stack was implemented like before I joined by Zester, when like at the beginning of the rewrite for the second version. So, and it's been here ever since. Worked pretty well. I think the main refactor is when it used to not have this control over the main event loop or the main thread. So we usually before you could pull when it for events instead of when it feeding new events. So I had to refactor things so that before the play states each would have a loop inside themselves. So I had to refactor them to pull the loop out and then add a tick method to them instead of letting them control the main loop. And so this is where we tick. So we can look at the main game rendering, which is in session. So these spans are used for Tracy. I believe that was discussed previously.
Yeah, being able to like track the time inside of Tracy that, or I guess track the time that a certain function will take. So in this tick, I feel like I've read through it once. And like, or just kind of like gotten a gist of it. But in the tick, there's a lot of different things that happen on like the data side, on the networking side, on the input side, on the graphics side.
Yeah.
And so I guess this is sort of like the entry point to where graphic stuff happens. I'd imagine graphics is probably the last thing, right? Like updating the frame.
Yeah, I believe so. So these updates hitboxes. Those are debug hitboxes. That it looks like this happens at the beginning of the frame, but probably not important. But that could mean that it is that they're a tick behind.
Interesting. Very curious.
Yeah, we could try to run the game and see if moving it down changes anything.
Yeah, would it just change like the accuracy of hitboxes? Or like where you expect it to be, maybe?
Yeah, so like if there's an entity that's moving, if we update the hitboxes before we update position entities, it's going to be the position. The hitbox is going to be based on the position of the entity from the previous frame.
Interesting.
I'm not sure if that's what this is doing. We might be. We might update the position lower down or something. I don't know. But I mean. But that's not something I was going to focus on, so probably shouldn't be distracted. Yeah. So this is where we tick the client, and then the client's allowed to return events that we handle, like it can return chat messages to which we can add to the HUD. You can get invite fleet events. So like this is like, so if you got pop-up that was like inviting you to a group and then it was complete, I believe this would change things. Or this might be if someone else accepted your invite, I'm not sure. Trade complete, printer updated, client disconnected.
Oh, this is cool. So are these the events that we saw at the Winit level, or are these like our internal? These are our client
These
events,
are our own events. So these are events that are defined by our client crate. So the client crate is front-end agnostic, so it can write different front ends over like Veloren or Veloren, and so it communicates things that happen by returning events from the tick method. So you call client tick, and then it returns a list of events that you can then respond to in the front end. Or like, client was kicked, so you can display a kicked message.
I see.
That view distance. I'm just going. Oh, I was compiling something in the background.
It has arrived.
So you can. This occurs when the server sends a message to force the client to use a specific view distance, and so you have it limited on the server side. And so this will just. We probably need to improve like the UX of this, because currently it's not really obvious. Like you try to drag the view distance up and it just like snaps back down and you're like, why is this not working?
Yeah.
So we need some sort of indicator that like indicates that this is the view distance set by the server. And also we probably don't want to save. We might want to have like either per server view distance configuration saved on the client, or just not save it when it's set by the server and just save what you previously had. But right now we just save it when it's set. It's the simplest way it works for now. Outcomes. I think there's a lot of stuff in there and a lot of potential for stuff to be added to outcomes. There's like sounds and stuff. I don't even know what all the different outcomes are. These are character created, character edited. It looks like we don't do anything for those. I wonder what purpose they have. And then if there's error creating a character, that's what saying this will be able to display a little pop-up with the error. And then finally we have map markers in your so I think someone recently worked on this, is allowing you to see markers that were placed by other players in your group, and so this can update them when they change their markers on the map. Oh, it's okay. So this is actually not the main tick method that it's called.
That's just the one that is like our data representation, or?
So this one is like mainly focused on ticking the client, and so it's sort of factored out of the one here below. So this one is the one from the play state trait. So the one from the play state trait is what we call in run. So, but this one we'll call the other one that we just looked at some point. So look for it. Yeah, it calls it here. So it's just like two different methods named tick.
Yeah.
And one is part of a trait, another one it's just like associated with the start. So I should probably get closer to the graph.
Oh, that's so cool. Got all the game input stuff there.
Yeah, this is. Yeah, these are all the inputs that So this is where we finally handle stuff like inputs from Winit. So we'll translate, before this, we'll translate keys into our like own internal game input event. So then it's easy to remap.
Yeah, I was just thinking like if we're hard coding that, then I guess we'd have a layer in between that allows people to change how it's getting called.
Yeah. This is okay. So I'm just gonna go through this quickly. This is just checking that the client is like an in-game player, basically, not like in the character selection screen. And so we do stuff with the camera. Get more stuff related to the camera. And then, so we need the camera to know what the cursor is aiming at, so we can get things that are being aimed at, like items and sprites on the ground, or entities that need to be interacted with. So we get if the client can build. So that's if we want to display like highlighting on blocks that are being pointed at. So building, is the client currently mining? So like if you have a pickaxe, and then here we get all the targets under the cursor, and then we use that to show like highlighting and stuff. And so then here's where we handle the window events. This is auto gliding, which will like adjust the glider to be optimal. This is automatic camera mode. And so the game can be paused if you're running in single player. So we check for that. And then this is where we actually take the client, using that other method that we looked at. And then debug info, this is just the debug info that you can show in the HUD. And then this is where we all the UI code is here. And then the UI can also generate events, and we handle them here. So we get events from Winit, and then we hand those down to other things, and then we take the client and we get events back from the client, and we also get events back from the UI when it's interacted with. Like if someone clicks like a logout button. And then here is all the data needed to render the current scene in the game. So it takes the whole client, so it can get any data about entities in the ECS, and also passes the client state, which also is where the ECS is. But so these can actually point to overlapping information. I think I tried to remove the client from this before, and so that you could run this without a client and like render things without having a client. But I think someone added it back in because they needed to get something that was easily accessible. So, I want to eventually it would be nice to be able to refactor it so you can generate scenes and render them to iterate on graphics programming and stuff without having to load up a whole client and connect to a server, because that has a lot of startup time. So it will slow down iteration, and also you have to include all that stuff when compiling, so that can make compiling take longer if there's extra things that you don't need. This is various settings, and this is where we maintain the scene. So the scene is like a level right above where the render is, and so the scene is basically like the glue in between the ECS and all the entities there, and then actually interacting with the renderer to upload meshes and other data to the GPU, and then actually gain that to be rendered. And so the scene is here. Okay, so I should go back to the other file real quick. The rendering actually occurs after the tick function is called, then rendering is called. So here's where render is called. and it's called with this drawer. So the maintain on the scene function will prepare all the data and make sure it's on it's going to be needed to be available on the GPU for the actual rendering for the frame. And the rendering is here, and so that is called from going back to run. So the render is stored in our window type. And so we get it here, we get a mutable reference to it, and then we start recording frame will generate this is where start recording frame is in the, like you can see down here, function source render.rs. And so this is where we start recording all the like commands to send to the GPU to render a frame. So first, like if it's minimized, we will skip it. And so there are various errors that can occur, and some of them we don't want to crash or anything or panic because they're just temporary errors. And so we'll just skip the frame by returning okay, none. And so this returns a drawer, which is a internal type of ours that helps to abstract working with the WGPU's render passes. And it has a lifetime in it because of how the lifetimes of the render passes work in WGPU. And this is if the profiler is enabled for profiling timings on the GPU, so how long it takes to do certain parts of the render pass, run certain rendering pipelines. So pipelines are basically like compiling the shader code with a set of settings that are integrated with it. So I guess I can use the particle pipeline as an example. I might look at that later. Okay, this is our particle pipeline, right? And so it just grabs a WGPU pipeline, render pipeline. And
is that like the default one that WGPU provides?
So this is the only one it provides. So, well, yeah, the only render pipeline.
Does that mean that you're not able to go and make changes to how you'd want the render pipeline to work?
And so it's how it works is configured when you create it.
Oh, okay.
And so this is basically a handle that points to the created render pipeline.
Okay.
So we'll create it here in the particle pipeline new function. So we get WGPU device, and then shader models, one for the vertex shader and one for the fragment shader, and then global layouts, which is so let me see if I can bring up the WGPU docs.
So yeah, while you're doing that, I think one thing that I find really interesting is like sort of seeing the breakdown of what the render pipeline looks like, because like in courses I've taken that have described it, the render pipeline is essentially, if I understand correctly, like what steps you're going to take as you're passing stuff to the GPU that has to do with everything in your graphics. So everything with lighting, everything with meshes, everything with shaders. And so you're kind of deciding how to put that together so that every frame it's able to step through in the process that you set up?
Yeah. So these are all the types, right?
Wow.
It's actually kind of nice. It puts them all at the like there's no like nesting or anything. It's like no hierarchy of modules on the public API. So it's just this long list, which is actually nice when you're working with it, because then you just do WGBU and then colon and then type in the type, and you don't have to like, import anything, because you can just refer to it directly.
Yeah, WGPU is
and
definitely
WGBU,
quite nice.
It's a nice short name too.
Yeah.
So we can go start with an instance. So this is like the entry point of WGBU. And like if you want, I can always hop back into Auctions code and show you where we use things like this. So you create an instance with a backend bit, just select like tell it what kinds of backends that you'll be happy with. And then once you have an instance, you can create an adapter. And then from an adapter, you can request a device. And then we can use this device to do various things like create bind groups, bind group layouts, buffers, random encoders, various pipelines. So a pipeline layout is what we were looking at before here. So global layouts, I think, includes a pipeline layout that we've created that's shared between a bunch of different pipelines. So actually, no, that's wrong. It is a bind group layout that is shared between a bunch of pipelines. And so we'll have a global bind group that we bind, and then when we switch pipelines, we don't always have to, which we can keep that bind group bound. So because it contains a bunch of data that's used in all of the different pipelines, not exactly all of them, but a bunch of different ones. So when if we ever switch between those, we don't have to rebind that bind group before drawing. And finally, we have this is the anti-aliasing mode that we're using.
And some of these things are changed by settings, I assume. So like when we pass in AA mode, that's probably changed in settings?
Yeah. So yeah, if you change that setting, we have to recreate all the pipeline. Because
so when we see, like, if you're in a game and you're changing video settings, and then you change one setting, it takes like 5 seconds to load, would that imply that it's rebuilding the pipeline?
Yeah, if it's taking any amount of time to do something after you change the setting in the graphic settings, then it's rebuilding pipelines. I've worked on moving the pipeline building into the background. It's not perfect yet, but it'll try to compile them in the background without blocking the main loop. And so these are actually these are compiled shader models that have already been processed, and the shaders will actually have configuration in them that depends on your settings. So let's see if the particle shader has any of those. Okay, so this is we have these experimental things which are just like checkboxes you can change. So this one will curve the world, and so like everything, all the vertices will be curved, and so that's why it's here in this vertex shader. They'll be displaced so that everything looks like it's in a curved world. So like if this setting is on, we will include this piece of this line. Otherwise, it's cut out of here, and so we have to recreate the shader, and then because we create the shader, we have to recreate the pipelines that are using the shaders. And so it's not like we're not super precise about like which pipelines we recreate, because generally it's better to be safe and just recreate a larger set of pipelines than like missing and accidentally not recreating something that should have been remade. But in a couple cases, I think we might try to skip some of the work in recreating pipelines. Are there any questions that have come up?
Not too much from the chat, I think. I've been looking over it. A lot of people very happy with Veloren's progress, of course. Callie asks, are we fixing bugs? And so, yeah, we're kind of walking through some of the graphics pipeline. We're taking a look at some, not really bugs, but we're looking at some optimizations in like the second half today.
So here's like, we're creating this pipeline. Yeah, here we create a pipeline layout. So pipeline layout is basically a list of the different bind group layouts that you're going to be using with the pipeline. So each of these is a separate bind group. And so this means that we have to have these two bind groups bound. So we have to have two bind groups that have the same layouts as the ones specified here when we have a draw call where this is the currently set pipeline. And then this here is so WGView render pipeline descriptor. This describes all of the settings that make up the pipeline that have to be specified when it's created. That includes a label for debugging, the layout that was created above. This is the vertex related thing, so the vertex shader, entry point for the vertex shader, and then the buffers. So you can have multiple like vertex buffers that need to be available. And in this case,
there are quite a few settings here that you change on like the descriptor, but I think what makes it sort of elegant is that I suppose like if I was thinking to how I've sort of done some pipeline stuff in the past, it's all very like line of like me declaring a lot of things, whereas in this you can define it looks pretty cleanly with it being a struct.
Yeah, it's a nice like, so see, it's like it's a function, so theoretically these could all be like you could just have like a long list of parameters passed to the function, but then you can't really tell what's going on at all. And especially with something really complex like this, having like a intermediate struct that you create and then you pass helps to document everything, because then you name all the fields that are being used. And so the particles have a vertex buffer and an instance buffer because they're rendered using instance rendering. So we have a mesh that's basically a cube, and then we render a bunch of instances of that for the particles. So this is something that I've thought about optimizing, but I don't think it would fit in a session like this as well as the other thing that we were going to do. Because so we could if all we're going to be rendering is cubes, then there's optimizations we can do that will be more efficient than use instancing of a cube mesh. But that will limit the capabilities of this pipeline, because right now it can actually render any type of mesh, like a bunch of particles of like other shapes besides a cube, even though we're only using it for a cube right now.
Okay, so sorry, just like to reiterate that, like because it's able to do cubes right now, we can do an optimization that will allow it to do cubes better, but it would reduce the potential in the future, or you wouldn't be able to make stuff that's not cubes.
Yeah, basically we could hard code the fact that we're rendering a cube into the vertex shader. And so instead of having a vertex buffer and an instance buffer, we can just we can put all the data from the instance buffer, so that's per particle data, into just a storage buffer. And then in the vertex shader, we can use the current vertex index to determine what corner of the cube it is, and then use that to place the index, and then we can just render just providing an index buffer, and then generate, like place the vertices where they need to be for a cube in the vertex shader. And then by doing that, then we can have a draw call that is that draws all the particles at once, just like doing instancing like we're doing now. But the way instancing is implemented on the GPU, if you only have a very small amount of vertices in each instance, then it will limit the it's not like designed, it's not optimized for that, so it will only like handle like one instance at a time, and there'll be a lot of free computation power that's not being used on the GPU. So by moving from instancing to basically generating the vertices in the vertex shader, we can render all the vertices at once, and then it can process a lot more at a time.
Yeah, okay. And so, yeah, okay, I think that's what you're saying, is you're just trying to get as close to what the shaders are designed to be optimized for as possible. Yeah, okay.
Yeah, I think like there's probably like benchmarks you can look at somewhere, but they're not super easy to find, but just with a simple search showing like the number of vertices used for instance, and then like how that compares to not using instancing. But like I think the break point, that like the point where it's fine is probably like around 256 vertices or something, where you're able to use most of the power that the GPU has.
Sort of like on this topic, I recently learned why it's useful to use atomics sometimes instead of mutexes. In that, like I was playing around with it, and it was kind of a cool little experiment to time how long it took to do like a million iterations with a mutex versus atomics. And so yeah, kind of in that vein of like what can hardware, or what can we allow hardware to do that hardware is good at, and like playing on those.
Basically just moving into larger batches. And we actually do stuff like that with bright rendering, which I worked on. So okay, then we have the primitive state, and it's a triangle list. All of our pipelines, I believe, are just triangle lists. So we're just rendering triangles. This determines which side of the triangle is considered the front. So the front is determined by if you like go and order the vertices that are supplied, like if they were supplied in a counterclockwise manner, looking at that face, then that is considered the front face if we use counterclockwise. And then, or we could use clockwise, and then the opposite face would be considered the front. And then here we select whether we want to call any of the faces of the triangle. So like if the triangle is facing away from us, this will set it so that it isn't rasterized. And so these are like if you have something like a cube, you don't want to render any of the internal faces of the triangle. That's just wasted time. So that's what that does.
Yeah, so nice and easy that you can just like set. You're just saying.
Yeah, but sometimes like if you want to like, I think with the trails that were added to weapons recently, that's just like a flat plane. So you want to render both sides of it, and so here we probably have none. And then.
But doesn't this render pipeline work for everything that we're rendering? So how would you have it set to like a specific cull mode for?
So this is for our particles.
So this is just a render pipeline for particles. Interesting.
Yeah. So each render pipeline will have each of these rendering pipelines. Will have some of the configurations here will be different for them.
I see.
Yeah. And then clamp that. That's not. Polygon mode fill. So this is like if we're just drawing like the edges of the triangle, we're filling it in. I'm pretty sure we use fill for everything. That's all we need. And then conservative rasterization. That's to do with the rasterization and whether like selecting certain pixels that are on the edge of a rasterized triangle are whether or not they're rasterized. I think conservative rasterization will probably anything that has even the slightest overlap, I believe it'll rasterize that pixel, and otherwise it uses some other algorithm. This is the depth stencil, so this tells WGPU what format of depth stencil we're going to be using with this pipeline. And we use a 32-bit flip depth buffer, and then whether this pipeline is going to be writing to it, and then what comparison. So use greater equal because we're using a reverse depth buffer, which allows more even distribution of precision across larger distances. And it basically like cancels out. So like with floats, you have a lot of precision like bunched up at the really small values. So this helps to cancel that out by reversing the depth.
Is it more costly to do it like this?
No, not really. Other than the fact that we definitely need a 32-bit flip buffer instead of the 24-bit one.
24-bit. Interesting.
I think also I think there's issues in OpenGL, at least on some versions, where so with this we want to use a range from 0 to 1, and some in older OpenGL, or at least without certain extensions, you can't. The range is -1 to 1, I believe, and so you can't really constrict that down to 0 to 1. And so because you want at 0 is where you have the most precision, and so you want that to be flipped around to be the farthest point. But if it's going -1 to 1, you can't flip that around and have 0 be the farthest point from the camera. If that makes sense. Um, so depth compare is basically when we rasterize pixels for a triangle, it will look at the depths that have already been written to depth buffer for those pixels, and then if this comparison fails, they will not those pixels will be discarded and they won't run the fragment shader with those pixels.
Oh yeah, because they're behind other stuff, right?
Yeah, and that saves a lot of time.
Mm-hmm.
And there's you can lose this optimization if you decide that you want to modify the depth in the fragment shader, which is like something you can do, but then you lose this optimization because it can't skip the fragment shader if the fragment shader might change the depth. And additionally, there is the fragment shader can discard fragments. So you can like say, I want to skip a fragment. And we actually use that for transparency once by using by skipping like fragments in a pattern so that only some of the pixels are rendered, and so you get this transparency effect. And we use that for like the main character when you zoomed in before. But the problem with that is that it will, because you're discarding fragments, there's two issues with this. One of them is that it can't predict that you're going to write to the depth for those fragments because you're discarding them. So it can't like preemptively start rendering other stuff that's going to be overlapping that. It can't like preemptively discard other triangles that are being rasterized behind that, because you might discard a fragment and the depth won't be written there, and so then whatever you're rendering behind it will show through. And so if it wants to be able to render that correctly, it can't optimize it by doing all of that at once. So it first has to run your fragment shader for all those fragments that can cover the fragments of a different triangle behind it. And so this getting the GPU to work quickly is all about laying it to as much as possible in parallel without any dependencies that can be introduced by doing stuff like discarding fragments. And then another issue with discarding fragments, especially like for transparency, where you'll do it like alternating, is the compression of the depth buffer. So the depth buffer can be sort of compressed on the GPU. So like if a bunch of depths are the same, it doesn't really have to do as much work to query that depth in the area, because it knows that like if the triangle is overlapping part of the depth buffer where it knows all the depths in the area are a certain amount, then it can discard a large amount of fragments at once without having to do as much work per fragment. So if you start alternating, like whether or not you're drawing pixels in one spot at a certain depth, that'll ruin that compression. And so then drawing more things on top of that can be more expensive.
And just a quick question from chat: do these shaders support negative light like Blender?
These shaders support negative light. So you can use negative values in the shaders, and then depending on what attached texture is being written to, that'll either support negative values or it will clamp them to 0, I believe. I think there could be bugs that cause it not to be clamped to 0, but I'm pretty sure I've seen something that says that it should be clamped to 0. If it, like, there could be bugs that like cause strange things happen instead of clamping it properly. But usually it should be clamped to 0 if that's the like minimum supported value for the texture type being used. But I think we use float textures, which would support negative values until like the final step. but I don't think we really have any negative light values. So this is a stencil. We don't use that currently, and bias with that. We're not using anything there. This is multi-sampling. So you provide how many samples you want, and then so this is telling the GPU what for multi-sampling the target texture is using. And currently we only use one here because we disabled MSAA because it doesn't interact as well with some optimizations that we did in terms of 3D meshing, I believe. Yeah, it doesn't work as well with optimizations from green meshing, and you can, when we use MSA, there's a lot of, you can get gaps in between some of the quads that are used to render the terrain, and then those will show up. I think there's a way you can detect those and remove them, but there's other issues with MSA. Is like, so we can render, let me see if I can just run the game. You show an example. But basically we can render like a bunch of blocks together as like one giant quad, and then we can pull the different colors from the texture. But because that MSA works on the edges of triangles, so when we're rendering all of our
Oh, do we have a server browser now? Or has that always been there?
That's been there for a while. It just remembers it just remembers servers you typed in.
Okay.
Hopefully this will connect, but it might not.
Cool.
So like this like section of blocks could theoretically be one single pair of triangles that make up a quad.
Yeah.
And so this edge in between them, MSAA has no way to act there because that's not actually an edge between triangles. So if we're using MSAA, you would see aliasing there.
Interesting. Okay.
But I mean, I think there might be a way to get around that by like doing some like anti-aliasing when we're actually sampling from the texture for these colors, but that could make it more expensive in that stage. And finally, there's the fragment related stuff. So the fragment shader, the entry point for the fragment shader, this is the targets that are going to be attached when we're drawing with this pipeline. So the textures that we're drawing to basically. And so we have a RGBA 16-bit float texture. So that's 16 bits per color. And then this is the blending. I believe this is left over from when particles used to be transparent. So obviously there's a lot of issues with transparency, so they need to not be transparent, but this would be able to blend in together if they're transparent with the color that's already in the texture. And then this is a write mask, just think what colors we're writing. We don't use this for anything, so we just write all the colors. And that's the pipeline generation.
One thing I'm curious about with this pipeline is what is like one thing in this entire struct of config stuff? Which one thing that if you changed, it would look like the most radically different?
Probably this.
Interesting. Well, and what could you change it to? So instead of fill, like,
let's see. Change it, probably like line. Yeah, line.
So you can make, instead of all particles being like filled in, you can just make all like a wireframe of everything.
Yeah, I believe so.
Oh, that's really cool.
Okay. Well, we have to recompile. This is shader change.
But if someone wanted, they could add this to the in-game settings.
Yeah. I don't think it would be useful.
Yeah. Yeah, it's like one of those filters that you just add for the sake of it being cool and not necessarily something that people would use.
We could also remove depth writing. That could probably cause some strange stuff. Because then like things behind particles could be drawn on top of them.
Oh, interesting.
Depending on the order of drawing.
It would be like sort of random whether or not stuff is drawing on top or behind.
Yeah, it'd be like depending on the order of our draw calls.
That's pretty cool.
So I'm trying to compile that. We'll see how it looks.
Yeah, I'm interested.
I think a good thing to look at would be the drawer struct, which is part of our abstraction that we built on top of WGPU to make drawing easier. Go to here, and it involves some lifetimes. So you have this enum here because we want to start drawing the main menu before we finish creating pipelines. It's on Vulkan, it's fairly quick, but on like DX11 and 12, it's kind of slow. So in the background, we'll be creating pipelines, and once we create all the pipelines needed to render the UI, we'll just go ahead and return those to the main thread. And then when we get to here, we will be using this enum variant to indicate that we have those pipelines available. And then once we get the rest of them, we'll switch to using this. Yeah, so this just gets like the UI pipeline, and it'll get it if we're in either of these states or the book pipeline. So the UI is what we use to draw the UI, and then this is what.
One thing I'm curious about is we've seen like a decent amount of stuff with the pipeline, how pipelines are set up and like stuff is sort of processed a little bit, but we haven't seen very much about like how stuff gets passed into pipelines, or like, so now that we have the pipeline, like how do we use it with like the rest of all the data and everything?
Can you repeat that?
Yeah, so like with the pipeline, like the pipeline will let us draw things in a certain order in a certain way, but then presumably every frame we're going to be sending, we're exploring particles right now, so we'll be sending some amount of particles, some quads, some vertices, and all of this kind of stuff. And so where is like the connection between all of that, like the data that we have in our representation and how we actually pass it to the GPU?
Okay. Yeah. So the particles, that's mainly through the instance buffer that we create for them. So Yeah, here it is. So there's this information that we have per particle. And so we have when it was created, lifespan, source of randomness, the mode. So that's like what type of particle it is, which you can see here. And then the direction the particle is moving in and its starting position.
Mm-hmm.
And so we can create one of those, an instance here from these methods. And then we'll pack all those into a buffer and upload it to the GPU, which I should go to that in a second. Yeah, the other thing I want to look at is the vertices. So the vertice type for this is just a position, and then the normal plus ambient occlusion, which really doesn't apply because we're just using cubes for this. And those are just packed into 32-bit. So I wonder if I can find where we create the cube mesh. Let's see here. We might create it in the particle scene. Don't create it here. This is the model that we're using. Stored in a model. It looks like that we actually have a cube model voxel file that we are basically loading up like a figure and meshing it.
Instead of just using a very generic cube?
Yeah, instead of just like hard coding it like here, or just like putting in some coordinates. So I guess we could change that. Could open it up in Magica and change what it looks like if one keeps to look interesting. Let me do that real quick. Actually, if I can find where I have the voxel editor.
All good.
Program somewhere. Yeah,
I'm just taking a look
at a random.
Oh yes,
in a random folder on my desktop. What?
Yes, there's no bugs in Veloren, just really big spoilers, says Cali Cats.
Oh my.
Lots of love in the chat for Veloren. Love seeing this. We also have, I think this is Spanish. I'm gonna look it up. I think it says the best game in history, but El Mejor Juego de la Historia. Translate. Let's see. Best game ever. Oh, very nice. Oh, then a response to C. Yes, very good.
Okay, here we go. This is our particle model.
Mm-hmm. So it is just a super generic. We can just make a unit square.
Yeah.
With how it with it loading in a Vox file and using this, other than like loading and stuff like that, does it actually pose a optimization issue? Is it like trying to like look at this actual model consistently when it can just be looking at a unit square?
If we if we hard coded the same model, so that wouldn't change anything.
I guess it would make it a bit more clear though, just because it's so simple.
Yeah. But I think the intent when this was initially implemented was to allow like all kinds of shapes to be used. Although I don't know how efficient that would be. So see if we can make something. Oh, then there we go. And save this.
So are you changing the particle model to be that?
Yeah.
Interesting.
See what happens. And then, oh, okay. So I tried to run with that change to the polygon mode, but it didn't work because we have to have a feature enabled. We have to explicitly enable the non-fill polygon mode. It's not very common. And it's not implemented on all of the backends that we'd want to work that WGPU can support. So you'd have to request a feature. I should undo that change. Yeah. Try to compile again. But while we're waiting on that, I can go back to looking at how we're sending the data.
Or couldn't you just run the previous release build that you made? Because I don't think. Oh no, it would have been overwritten when you tried to, because it was a runtime error with the fill.
Yeah, it would have been overwritten.
Yeah.
I think so I'm building a receive auction version, which I think it uses a different profile. And I actually did build a version with just the regular debug profile. Which I can use single player on this. Yeah, single player is disabled on the other one, so that it will compile faster because it doesn't include a server.
Yeah, I think like one thing that I'm quite interested in doing is making like So I know you've done like some work putting like binaries together for very specific things, like getting like thereabouts clients to connect or stuff like this.
Yeah.
But just having other ones that are like, you load into like a very small default world with like just a character, super small, no world gen, no nothing. Because like even right now, it's still doing all the like economy simulation to get it loaded and stuff like that.
Yeah, it would be nice to like run Voxgen and then just have it like open into a world, no like character selection or anything.
Yeah, pretty good for testing.
Yeah.
I always imagine like if I was going to go and try to do that, I'd have to like, so there's like a lot of strings that are set up all over the place, and I'd kind of have to like tweak with some here and there and stuff like that.
Yeah.
But there's also probably a lot of references already with like the examples that have been made that are like, you can just do it like this sort of, or just copy someone else's.
Yeah. Just skipping character selection would probably be pretty easy to set up, because you could just have Voxgen just like select a character on its own.
Or like just even generating a thing.
That would be pretty simple to do. But like skipping parts of like creating the world would be even more complex. Or even like not having a server at all would probably be a little more complex to figure out how to get it to work. Since everything's all like wired up for this client to connect to a server and such.
Oh wow, it's happening.
Oh yeah, oh look.
It looks like the bees are making music or something.
Yeah. It is significantly more vertices than before, so
wow. That looks so cool. Yeah, it has like a whole nother effect sort of. It like a lot more like snowflakes like that.
Oh, I broke something. Oh no, this just finished compiling.
Okay.
We have a bunch of debug information. And we can actually see how.
Oh, GPU timings? Oh wow, I didn't know we could do that.
Oh, you didn't? Yeah.
This is a cool setting panel. Holy.
Yeah. There's this crate called every GPU profiler, which makes it pretty easy to set up profiling of different things using WGPU on the. And what it'd be nice if we could integrate this into Tracy, which would be possible with the new version.
Like all of the stats that it's exporting?
Yeah, like this data that we have here. We should be able to send that to Tracy. In the latest version, someone worked on adding a raw C API for giving Tracy this information. So that would be nice once it trickles down to the Rust crate. Looks like it's starting SpaghettiOs.
Yeah, I was gonna say, it'd be cool if the snow particles were modeled as snowflakes. I feel like that would be like difficult just because they'd have to be pretty big snowflakes.
Yeah,
maybe they could be smaller.
I could shrink them, but I mean, the more detail we add, the more vertices there are, and that will slow down things.
I think it's like definitely
right
like
now
the constraint of like the constraint of making everything in the world everything is cubes. The constraint of that gives it like a really cool looking aesthetic to the game. Whereas like making stuff look more realistic is definitely like one way to go, but then harder to optimize and all of this.
Yeah, and just generally expensive with more detail per particle. But so right now, about a millisecond of time, and there are 7,000 of them.
Yeah, which is crazy. Like just to think that just idling.
And we list how many are visible, which kind of confusing because we don't do any calling out.
Oh yeah, so that's like one optimization that could be done is like calling these particles.
Yeah, I don't know why we're displaying this though. But
wouldn't WGPU do that for us, or do we have to manually cull it ourselves?
okay, so there's like different levels of culling. So culling that we could do is just issuing like a draw call at all for particles. But right now, all the particles are a single draw call, so there's no way that we can cull them unless we broke it up into multiple draw calls for like each region that they could be in, or something like that.
So if they're in a specific chunk, like chunk column, then you could like set that as its own draw call, sort of.
Yeah. Well, we'd have to break up. So right now, all the particles are in a single instance buffer, and the optimization that I was thinking that we could go through is, so right now the buffer is recreated and re-uploaded every frame, and something that we could do is, instead of recreating the instance buffer, we reuse the existing one and we just update it, which could potentially be cheaper. Ideally, we would not re-upload all the particles every frame, but that it would be more complex to implement. So I don't think I could like do it in a short session.
Yeah.
So but we could do that by like having like chunks of the particles, like not like in the chunks in the game. So like it's like we have a certain amount of particles that we upload, and then that's like in a large enough buffer that it's saving you time by not having very many draw calls to render different buffers full of particles. And then,
but if they were in a chunk, then wouldn't we be able to cull that more easily because we could see what chunks we're looking at and then just say, don't do this entire draw section?
Yeah, we could do that. But the thing is, if we're continuous, the nice thing to be able to do with particles is have a bunch of particles that were created at the same time, all together, like contiguously in a buffer. So then you can just render that and you don't have to upload to that part of the buffer. And then you can have like other parts where you're uploading like all the new particles for a frame. But that wouldn't be spatially separated, so we wouldn't be able to call it like that. So I guess there's some trade-offs there.
Mm-hmm.
And yeah, so right now the particles on the GPU take about 1 millisecond, and it's you see there's like not much of the screen's covered in particles, so most of that is probably in the vertex shader.
That's so cool.
So I can take us. This is the maintain function. This is where we take go through the ECS and we like look at any like bodies, so like any of these bodies that will emit particles, like campfires probably, and then any like character states, like attacks that are emitting particles, like flamethrower attack, or any beams. So beams, I believe, are separate entities, so that's why I go through it here instead of as part of the character state particles. And so a lot of beams are made up of particles, and then block particles. These are like where we have the snow appearing, or like trees with the leaf particles that will like slowly float down. Those are generated here. And then particles from shockwave attacks, particles generated by auras, and then particles from buffs. And so like a buff is like if you're on fire. and then you'll have particles coming off of the character.
Interesting.
And so
ever use case that, well, of course that we use right now, but in the future, like let's say there was something like we added waves to water or something like that, and we implemented it with particles, then that would probably be a new system here.
Yeah. Well, yeah, it'd be just like a new method here. That we just add a method. And then so the method takes scene data, which includes all the ECS. I'll reference all the ECS state. And then see, like here we get the ECS out of the state. And then we iterate through all the entities that have a body, position, and velocity. And then we're like, if the body is a lit campfire, we'll generate campfire particles. And etc. And so all the particles, this particle manager just keeps a vec of all the particles. And then so all these methods will just push new particles onto this vec. And then at the top of maintain, we will retain all the particles that are still alive, and then add more particles, and then upload these particles to the renderer. Unless if particles are disabled, then we will just remove them all. And so here's where we upload the particles. So this is essentially it. Interesting. Yeah, okay, so it creates it. Yeah, it takes all these instances of the particles. So it'll iterate. It iterates through all the particles, and then it will map that. So each particle contains this particle instance, which I believe is that just the instance data that we looked at earlier. And then it will plug those into a new vec. And then using the slice from that, it'll create those instances and upload them to the GPU as a buffer. So here we're creating a new buffer, and there's like a to-do optimized buffer. So that probably includes not uploading all the particles, re-uploading all the particles every frame. But now I would like to not recreate the buffer.
Yeah, so this is like sort of like the optimization that we'll go in and like do a little bit of work on right now.
Yeah. Yeah, and then we sit here, we set self.instances to the new the handle for the new instance buffer, and then so this was implicitly will drop the old handle. So to do this, first we're going to need to look at what instances affects instances type. So instance is something that can be updated. Okay, it can be updated. It's created with the dynamic buffer, so that means we can update it. We have a to-do looking like, should we make this less dynamic? So we can update it with this method. So basically, if existing instances buffer is large enough for the number of particles we have, we should be able to use this update function instead of creating a new one. Let's first look at how we create a new one, though. So to create a new one, it creates a new instance buffer, then updates it. So it's just blank and it updates it, and then it returns that. So We have a method here to update instances though. No, we don't. So I need to add a method. So okay, so the reason we need to add a method is because update function takes a WGPU queue, which we have inside our renderer, but it's not exposed because we want to try to encapsulate it a little bit. So it's not exposed, so we need to add a method to the renderer that will allow us to update instance buffer. This probably doesn't need take. These values we want to use, and then we'll also need to, I'll put that first. We'll need our current instances buffer. So and that would be really fun. Since we need a mutable reference here. And then this should just basically call the same thing that's here. Offset. Okay, so offset is where we could upload. So we don't have to like upload a whole buffer. We could upload like part of it at an offset, but we're not going to do that. The offset is just going to be 0 here. And I think that's all we need here. And we have a way to get the amount. Okay, we have a way to get to the length. So we know if it's not. I wonder though, how do we handle if this is longer than, so if the right slice is larger than the buffer, I wonder how that's handled. So I'm gonna look at that.
Oh, I muted my mic a while ago. I don't know how long you haven't been able to hear me for.
Oh,
wow. I was curious, what with the function that we just wrote, the update instances, what's the difference between that one and the one that came before it?
So this one creates a new instances buffer. So that,
oh, okay.
Well,
so it's sort of like we're cloning it and making a new one.
Creates a buffer.
Mm-hmm.
We're not cloning anything. We create the buffer and then we upload the slice of data to it.
Yeah.
So yeah, to create it, we use this create buffer name. Interesting. Okay. So yeah, but this is what the creating buffers do. And we store the length ourselves because we can't get that from the GPU. Okay. Go back. Trying to remember what I was doing. I was looking at this update function. Oh, I want to know what it does with the sizes. Too small. It looks like it doesn't check it, but I know WGPU will check this and it'll panic if it's not the right size. So that's okay, so we have this update instances method. So now we can use it here. So essentially, we can check the length here. We can say if we have enough space already. And equal to the new of instances. And we will, then here we can just upload the data to the existing buffer. Otherwise, we can create a new buffer. Under that update. This works. It should be a very simple change.
So we're basically just checking if the size of the buffer that we were trying to like update with is shorter or equal to what it is currently. Then we can just fill out the data. Wouldn't that leave garbage data at the end?
It would, but when we render it, okay, so the rendering does use the length of the buffer that we've stored internally. So we need to change this draw method.
So because we're storing our own length. Oh.
Well, okay, so we're storing the length of the buffer, so that won't change. So we would render the garbage data. Although particles, once they have like gone to the end of their lifetime, I believe they probably depends on the shader, but they might just not render anything. But it still is not a good idea to try it. So here we want to pass the length that we're going to render. Unless actually, so pull up that method, the draw method. So draw. I can close this. So we use these drawers to abstract working with pipelines and render passes from WGPU. So scene works with these drawers, and then the drawers interface from the scene into WGPU for issuing draw commands. And so there's several. So we have 3 render passes, I believe, besides shadows and stuff. The first render pass, and then second, which is just the clouds, and then actually this also includes trails because we render those after the clouds for transparency reasons. And then finally there's the third pass. But we also have bloom, which is actually multiple passes because so a single rendering pass is going to be rendering to a single like texture target. So initially we render in the first pass, we render the terrain and similar stuff like figures and stuff all to first texture, and then we will sample from that in this second pass and render to another texture. So you can't like render to a texture that you're sampling from. So here in the second pass, we're drawing clouds. Clouds will read from the depth buffer from the previous render pass and use that to determine do like cloud rendering depending on the depth of each fragment. It can sort of trace array to that depth and then sample the cloud density to render clouds. And then we also draw trails here. And then in Bloom, so Bloom is all about blurring. So you're going to need to be rendering from one buffer into another. So Bloom will it'll sort of downsample to a more coarse buffer and then upsample that back. And during that, it'll use a sampling kernel that'll blur things as it does that. By sampling from nearby pixels. And then finally we have the third pass, which is where we're doing post-processing, and then the UI goes on. So post-processing is we take all of the in-game world rendering, and then we will we'll take the high color depth and map it to 8-bit color depth, and probably do a few other things like there's like a screen wobbling effect that you can see underwater. And I think it might be optional. I don't know. Or experimental.
Optional as in like you could turn off in settings, or
it might be an experimental thing. I don't remember. But yeah, anything that like is just processing that applies to all. This is where we have the anti-aliasing. So removing the pixelated edges of things. And we also, if we're taking a screenshot, so instead of rendering, so here we're rendering to the surface texture, which is the texture that is basically the window. And if we're taking a screenshot, we'll actually render to the screenshot texture instead, because you can't download the surface, you can't like read data out of the surface texture. So instead we will render to a different texture, and then we'll take that texture, send it to another thread to be downloaded onto the CPU asynchronously, so it doesn't block the main thread while we're downloading it. And then we will, but we'll also render from it to the screen. But if we're not taking a screenshot,
or sorry, when you say download, do you mean download from the like GPU because it has it in its memory?
Yes. Yeah. So we'll download it here. So we have this screenshot function, which is basically a closure, which is provided by, it's provided like at a much higher level by, I think, encode in the window code. And this is the code that will save the screenshot, and it'll also like print out or send a message to your chat box that says that you took a screenshot. The code is in this closure. And so, but we use this closure so that it can all be done in a background thread. And so when you take a screenshot, we need several things. So we'll a bind group. So this is the bind group for the texture. For blitting. So we'll take, what we do is we take the screen, we render to the screenshot texture, and then in addition to downloading it in the background, then we will blit it to the surface texture basically, which is just like we render a giant triangle that covers the whole screen, and then each fragment we just read in the value corresponding on the other text, the corresponding value on the other texture. So it's just in terms of blit. And then this is a texture view. This is, I think, one of these handles is what we're going to use to download the texture. And then buffer. So, okay, so we have to copy the texture into a buffer and then download it, because we can't directly download the texture. And then there's that screenshot function that I was talking about. And then we need to know the width and height, because we need to know what size we're copying and downloading. And then we need to know the bytes per pixel and the texture format as well.
Do we not have a like a constant bytes per pixel? Like what might make that change?
Well, it's just so that this is it can change if the texture format's different. I think I used to not have this texture format here, but then there's some other stuff like the ordering of the different colors.
Yeah, that makes sense.
Depending on the texture format, so I couldn't do this, but so this might be able to. We could probably derive this from this, but I still have it there. Yeah.
Yeah, there's way more
But
to
it's
taking
not
a
constant
screenshot than I
because
thought.
if the format changes. And so I think we typically will be using the same format, but not all of the time, because because we can render interchangeably to the screenshot texture or the surface texture. They have to be the same format, because the pipelines that we use for rendering, we tell it what format we're going to be using when we create the pipeline. So even if we wanted to, so if we wanted to have this be a fixed texture, we need to fix the texture, the surface texture. And typically we will always have the same surface texture, but that's not always true, because I believe on different platforms, some texture formats are better, and we allow WGPU to select the preferred format that will work. So then that means the format can be different here. So we have to account for that. And also it just makes it more like modular. So we don't have to like worry about the global details. Yep, so this is just creating everything that we're going to need to take a screenshot. So we need to have a texture ready to render it into and stuff. And here's where, okay, here. Where do we send it? Okay, copy to buffer. So we figure out how many bytes per row the texture is, and then we use this copy texture to buffer function on the encoder, which will copy the so this doesn't actually do anything, it just adds it to the list of commands that we're going to submit when we submit the command encoder. But it'll tell it that it needs to copy the data from this texture that we're going to render into a buffer. And actually we used to have a bug here, because there was sort of a race between this new thread that is created right here. So this, and when this copy occurs. So I believe, I don't remember the details.
Like it would assume that it has the data before it was written, like the data was written.
Yes, and there was an issue with that, because, okay, I remember. So in this function here, we will map the buffer so that we can read from it onto the CPU. But if you have a mapped buffer and then you call it and then you try to copy into it, that's an error. So there's a race between when the encoder is actually submitted to WGPU and when this background thread requests WGPU to map the buffer. So if the request to map the buffer goes in first, that causes an error when this is submitted to the queue, and then WGPU will return that error and panic. Yeah, so that was because it's a race between like things happening on two different threads. It didn't happen all the time. Yeah. So it was a little hard to find.
I imagine.
So yeah, but this creates a new thread, and in that thread it calls this, which basically will map the buffer. So this, we can run this on our main thread because we're just doing this command. It doesn't cost, it's not actually like doing anything, so it doesn't cost us time. It doesn't block anything. But here's where we actually have to block. We have to block for mapping the buffer. So if we properly are copying the texture into the buffer beforehand, mapping the buffer is going to have to wait on that to finish. So we will block right here using this buffer mapping feature. And to do that, we create a single threaded Tokyo runtime. So it's just using the parent thread and we use it to block.
Interesting.
And
actually, just a quick question on that. So if we're using a Tokio runtime for this thread, does that mean that we have to use we have a Tokio runtime running for all of Veloren, or just we started up for this thread?
So we have one running for other things in Veloren, but not on this thread. This is a new thread we created. So we're controlling this thread, not Tokio. And
interesting.
So when we call block on, then Tokio gets control of the thread, and it'll wait for this future to complete, and then it'll return back to us.
In my mental model of Tokio, I always thought that it was like once you use Tokio with your application at all, it's like infected the whole thing. Now it's all Tokio. But it's interesting. It does make sense. It's like, oh, you have a different thread running. Then yeah, why not just have that be its own runtime that's separate from the rest of what you're doing?
Yeah. And there's probably like a simpler like async basically like an engine.
Oh, like standard library async, you mean? Or
no, like another create like pollster would be simpler to use here, but Tokio, and it has the ability to create it for the parent thread, so it's not that much of an issue to use it here than something simpler. And so then we have the block on that, and once that's completed, then we are allowed to, I think this is a slice that we can read from. No. Okay, so this is, I think this is a WGPU type that we can use get mapped range. This slice here. Oh, this is something we're returning. It's not coming. Unit. Okay, so this is where we copy from the mapped slice, and then eventually we will convert that into an image using the image crate. And so here, when we're converting to image, we need to know the layout of the pixels and how many bytes they are, so we can have the proper, like, the image can be saved properly. And then we will pass this image to the screenshot function, which does whatever it wants to do. And that's how screenshots work. Anyway,
nice. That's pretty cool.
Yeah. So that's the third pass. And then the UI is drawn. The UI is drawn after post-processing. And we have optional. EGUI uses its own rendering pass because that's how the crate is currently set up. I believe this doesn't actually have to be its own rendering pass, but it's not like significant enough.
That's how we have it doing stuff.
Worry about refactoring it. And this is where we draw shadows. So all these methods are for different render passes. So, and the distinguishing feature for different render passes is basically what we're rendering to mostly. So this is drawing shadows to the shadow buffer that we'll later sample from when we're drawing terrain and stuff. So we can clear shadows. And then, okay, finally, this is the drawer type. Okay, this is the drop implementation for it. And okay, when we drop is actually when we will submit everything to the queue that we've recorded. And also when we handle the actual screenshot. Yeah, this is when we'll copy the screenshot to buffer, we'll send that out. And then right here is where we submit things to a queue. So the race condition we had is basically the thread started here versus this being called. Before. And see how we have the profiler right here? This actually is like why the bug I talked about earlier was more likely when you had GPU timings on, is because see, then it would delay right here before we got to this. And so it would have more time for this to call the map buffer in the background.
And so what's the way to fix this? Is it to like send a message to the other thread once it's ready?
The fix is yeah, this is the fix right here. So instead of starting the thread right here like we did before, we have this return a function that we will call here after we call submit, and then this will start the thread. So
okay, so it's just like ordering properly.
Yeah, so here we return like a closure that can then be called once, and that's what will start the thread here. And that was the fix. So for each of these passes we have a drawer type for each pass, and then that has methods to draw using like certain pipelines. So I'll skip over the shadows and save some time. So like the first rendering pass, we have like a method to draw the skybox, which sets the pipeline to the skybox pipeline, and then sets the index buffer that we might need to draw that, and then draws the vertex buffer, and then calls a draw call, which will use all these state that we've set here. And so each of these methods helps us manage the state of like which pipeline is currently set and like which buffers are currently bound. And so we can represent some of that state which type of so we can manage some of that state by having these new types for each pipeline. So we have a draw type. So pipelines where we want to issue multiple draw calls will return a drawer type for that, which has some lifetimes in it. And so that will then have its own method to draw different figures. But using this type, we know that the current render pass is set to the figure pipeline. And so that using that, we can ensure that we don't have to like reissue the set pipeline call while we are drawing a bunch of figures. And the same thing with the index buffer here. So we do that with a bunch of pipelines where we'll have the potential for multiple draw calls. And that helps optimize by not having a bunch of set pipeline calls.
Interesting. Do we track at all like how many draw calls are happening, or is there like a way that we could like visualize that sort of?
We do not track that.
You'd have to probably like advanced graphics stuff.
What?
Like I imagine like there's like some pretty advanced graphics tooling that is like catching stuff as you pass it to the GPU so that you can like do analysis on that. But
yes, there's some profilers that will like AMD has a profiler that's really nice. I've used it before, but it doesn't work with the GPU that I have on this machine.
Unlucky.
Yeah, so I have to borrow a laptop that has it's an integrated AMD GPU, but it's a lot newer than the one I have here, and it works there.
I have like an R7 or something like that. I don't know exactly. R520. I don't know. But could I install the AMD profiler and then look at it pretty easily on Linux?
Probably. Yeah.
That's very cool.
Actually, you remember someone was trying to use it on Linux and they might have had issues, but I don't know if it's just their GPU or if it's the profiler. But you could probably get it working. So I'd hope.
Yeah, that'd be cool to do a
the one machine that I've been able to use on is Windows, so I don't know.
Oh yeah.
So like this figure drawer, we know the currently set pipeline is the figure pipeline, and then we only need to set other things. And in some cases, we take that we go another level down. I think with the sprites. I think with the UI is so we have a UI drawer and then we have a prepared UI drawer. So we know it's prepared because we've set these this locals by group. So we set a model. So the UI uses a single vertex buffer, and then we set the scissor. And so we know all these things are set. So we don't have to set them at the beginning of every draw call once we have a prepared UI drawer. And then, but for the UI, these things can change occasionally. So we have methods to change. Also, you might see these like this scope type that wraps the WGP render pass. And that the scope type is part of the WGPU profiler crate I mentioned before.
Oh, so does it allow us to just say, well, this is a thing, then it's being
so like
or something?
Let me find where when we go to draw the fluid, we'll use this method scope. So this creates scope called fluid, and then it needs to borrow the device to do some stuff. And what this will do is it'll issue like some sort of like start marker for a timing. And then when we drop this, it will add a stop marker to the render pass, and so that will create a scope that we can time on the GPU. And it's convenient because of the drop and pull. So you can just start it and then do stuff and then drop it when you're done, and then you can measure how long all of those like commands that you issued to the GPU during that scope take on when running on the GPU. And so we use that for each pipeline, and then we also have them at the render pass level, so we can see how long a render pass takes and how long each pipeline takes. And we saw that earlier when I was looking at how long the particle we're taking in the debug information. So I'm going to go to the particle drawer. So here is where we get the link from the model till it's the link from the instances. The model is just the cube or whatever shape that I made. Here's where we get the number of instances. And so we just get that from this instances type, which is just linked to buffer that it stores internally. And so we want to be able to specify this to be something that's not that, because we're not going to be using the whole buffer since we're not recreating it at the exact size that we need. But I believe that this might not work actually so for buffers, we have this model. I think for models, we have a submodel type where you can create from a model, and it'll include the range that you want to work with. So you can just say submodel and then give it a range of indices into the buffer, and then it'll.
That's pretty cool.
Then you can take this, and then if the draw function that we looked at before takes the submodel, then you can just give it the submodel instead, and that's a way to like abstract over specifying the length to render. But here, I think this instances type doesn't have this, so I think it'll be easiest to just add an extra parameter here with the length that we want. So, or we can even make it a range if that'll help later, maybe. So. Like that. And then we can go back to the drawer. Go to particle drawer. And that. And we need to be, and then again. And that should maybe work.
A few other things from chat here. Awesome stuff as always. Not only a great game, but great on sharing the knowledge. Very good, very good. Thank you, Nicolas. Hey, Empress, how's it going? Looking good. Got a making awesome game. Love to see it.
Okay, that's a. Yeah, and so the trace evocation here is just a shortcut. Here. We have currently lets you define various aliases.
Okay, so we're doing run bin Veloren no default features. Ooh, SimD, we going fast.
Yeah, SimD is a default feature, but we turn them off.
Okay.
And I think we expose it as a feature because there's some issues with the coverage analyzer, test coverage analyzer that interacts badly with certain usages of SimD. And then it uses the no overflow profile. So we're profiling the no overflow profile. Disables a couple things that are in the default, like development profile. because they slow things down a little bit. So we want to have it closer to how fast release will, like a release build will run, but not using, but we don't want it to be exactly a release build because that has other things enabled that take a lot of time for very little gains. So, so no overflow.
No link time optimization.
Inherits from the development overflow. And it disables overflow checks and debug assertions. So I was going to look at Tracy to see if we could look at the time differences before and after this, but I don't know if I don't think we will have time for that today.
Well, actually, how about after we finish up here, if you could write something for the blog, that would be super cool because then I can put it alongside the video.
I can get,
and you can
get some measurements later.
Yeah, that'd be awesome. Yeah, because I'm very curious on like this small change. I mean, once this finishes, it would be cool to just see like the diff that was added, but like how it has an effect.
Maybe we can go find a town and look at the smoke particles.
Yeah. If you just do home, would it bring you back to a town? Oh, so if this didn't work, what unexpected behavior might we see?
There might be missing particles or panics.
Would there be particles like that flash inside it, like in and out, sort of?
Probably not.
Oh.
Like if we weren't rendering all of the particles, then like some of the ones that are at the end of the buffer, we'd miss them. Or like if we had the wrong size somehow, we could get a panic if we're like trying to draw more, like a larger range of the buffer than actually exists.
Mm-hmm.
Or upload to a larger range.
I mean, it looks like it's doing pretty good. And yes, just a reminder for other people, we increase the size of the base particle, so that's why we're getting some funky stuff here. This is not because of the code that was just added.
You can sort of see particle shapes at the top.
All right. So for today, is there anything else that you want to cover before we sign off here?
Just to see if there are any questions.
Yeah, so we'll see if there's any questions in chat. And so just as a recap, so today we've taken a look at the sort of like the entire graphics well, not all of the graphics process, but sort of like stepping through from how we go from the window manager all the way to, well, I guess like the window thing to the inputs to handling events, and then what it looks like to set up the rendering pipeline for different things. And then we went through and did an optimization where instead of recreating the buffer for particles every frame, the old buffer is used as long as it can be. And so that's sort of what we saw today. I don't think I see any questions popping in the chat. I'm just checking other channels to make sure. All right, so yeah, I think that's pretty good. Yeah, this was super cool to see. I think definitely. I mean, I went into this thinking that like even after this, graphics would still be unapproachable, but it's surprisingly more approachable than I ever thought it could have been. And so I think that there's definitely a lot of room to sort of play around with like there's a lot of configs on how the rendering pipelines are set up, and so there's like potential to kind of mess around and like learn a little bit there, I think. But do you think for other people watching, like Imbris, what do you think are some potential areas that people might be able to experiment with or play with now that they've sort of seen this?
They could experiment with different areas of the particle rendering if they wanted to.
Yeah, so I suppose like you mentioned, there were some optimizations like as you were walking through some other areas to possibly consider.
If someone wanted to, they could put some time in thinking about how the particles could be optimized so that we don't have to upload all the particles that are live at once. And I'm sure there's like material that you could search on this. Other people doing graphics things.
Yeah, certainly a whole world to be explored when it comes to graphics. All right, well, cool. Thank you so much for running this Coder Reading Club today. It's definitely a super awesome topic, and it was pretty cool what you were able to explore. So yeah, thank you very much.
Yeah.
All right, and so we will be back in, I suppose, a few weeks. We'll see what the next reading club is. But yes, I'll see you then.
Yeah, I'll see you.